Hello everyone, welcome back to Rust Planet. I'm Rochandra and today we are going to discuss smart pointers in Rust. There are many different types of smart pointers serving different purposes. From this session, I will cover some of them. First of all, what is a pointer and a smart pointer? A pointer is a variable that stores the memory address of some value. We know we use them by indicating ampersand and also referred to as references. Other than referring to or pointing to some values, these references do not have any other additional capabilities. In contrast to simple pointers, smart pointers are not just simple references, they have special capabilities. Smart pointers provide additional functionality beyond raw pointers, such as automatic memory management, reference counting, and thread safety. Let us go over the simplest smart pointer called box pointer. We know by default Rust allocates everything on the stack. In this case, the variable will be stored on the stack. If we want to store the same value on the heap, we will use the box pointer. An instance of this pointer is created using the new function. This will make a new heap allocation containing the value of 1 to 3. The variable y is now a box smart pointer which is pointing to some heap memory containing the value, and still the variable x will remain in the stack. Let us create a reference to it. Like variable y, the variable z is also a pointer. However, it is pointing to some memory location on the stack while y is pointing to the some memory on the heap. Let us go over some use cases of box pointer. Consider an enum called list which has two variants of cons and nil. The cons variant has a couple of items with it, an iterative value and the list, while the nil variant do not have anything attached. The idea here is to have lists which may contain other lists. Let us create an instance of the enum in main. We will define a cons variant with a value of 1 and another list with a cons variant. Finally, we will end the list by mentioning the nil variant. We are getting an error stating that recursive type list has infinite size. Let us explain what is the potential issue in this case. For the cons variant, we will mention two things. There is an iterative and another list which may be a cons type or nil. If it happened to be a cons type, then again we will mention two things. This continues until we mention the nil type. This leads to a recursive type, meaning a type which contains repeated instances of itself. The problem with the recursive type is the Rust compiler is unable to know the exact size of the instance at the compile time. The Rust needs the size of our variables at compile time. However, in this case, the size of the variables list cannot be determined at compile time. To further understand this, let us see how the Rust will decide the amount of space it needs to store a value of a non-recursive enum. I am defining a enum with four variants for explaining this concept. To determine how much space to allocate for a variable of convenience type, Rust goes through each of its variants to determine which variants need the most space. The first three variants of car, train, and air are all I32 types, so they need fixed memory space. The final variant, which is walk, does not take any memory. So the maximum amount of variable of type convenience will occupy will be equal to the memory space taken by the I32 value. In contrast to this, when the Rust tries to look for enum of list, the Rust know that the nil type will not take any memory space. However, It is unable to compute exactly how much space the cons variant will take. This is because the first value will take a fixed iterative value, but the second value is itself a list where we do not know in advance how much space it will take because it is a recursive in nature, meaning that it contains repeated instances of itself. The solution in this case would be to put the cons variant behind some type of pointer. The compiler tells us exactly this. The compiler now knows that the exact size of variant for this first variant. It knows that it will contain an iterative value and a size of box which is equal to the size of simple pointer which is of fixed size. Finally, let us fix this code in the main. Yeah. Now let us print the list in the main and execute. The list has been printed. We know that calling the new function for the box creates a new heap allocation. If we look at the enum, we may note that in case of cons, we are always making a new heap allocation by calling the new function, irrespective of whether the next variant in the list will be a cons or nil. The nil variant does not need a heap allocation since it has no data associated with it. We may note that the last variant of nil is unnecessarily being boxed or in other words assigned heap space. This can be fixed by reversing the enum definition. We can further wrap the boxed list inside an option. Remember that the option has two variants of some or none. When we have a further cons variance, we will have some boxed lists, and when we want to terminate the list, we will use the none variant. This means that we do not need to have an explicit second variant of nil. The nil will be indicated by having a none variant for the cons. Yeah. Let us modify the code in the main. We will wrap the cons variant by sum. The last variant does not need any heap allocation. This implementation is now more precise and efficient. Let us look at a couple of more cases where the use of box will be beneficial. Box is also useful when copying the large amounts of data when transferring ownership. Let us define a structure called useData. Next, we will define an instance of useData called a data1 and define another instance of useData using the box pointer called a data2. We will also define two more variables and set them equal to data1 and data2 respectively. The ownership of data1 is now transferred to data3 and the ownership of data2 is now transferred to data4. When transferring ownership, the data is copied around the stack. So, in the case of data1, the entire data will be copied because the entire data is residing on stack. However, in the case of data2, only the box pointer will be copied, which is small amount of data. The actual data is not copied or relocated to some other place within the heap. In this case, does not really matter since the struct does not contain something substantial. But if you imagine huge data stores a lot of information, this will have a significant impact. Let us look at the another use case of box pointer. Consider that we would like to create a vector of different types that implement some trait. To simulate this, I will define a storage trait which will be later on extended to provide storage related functions. Let us implement this for huge data. Next, we create another type called small data and implement the trait for it. In main, we create an instance of small data. Now, let us assume we would like to define a vector of types that implement the storage trait. Yes, this gives an error of mismatch types. It further elaborates that expected struct box use data. However, it found struct box small data based on the first two instances of the vector. The rest detects that the type should be boxed use data. However, the later on instance does not conform to it. Remember that vectors can only store values that have the same type. To enable the vector to store different types, we can tell the compiler that store any type in the vector that implements the storage trait. This can be mentioned using the trait objects. So let us set the type annotation. Remember that the trait objects need to be stored behind some type of pointer. In this case, we use the boxmart pointer. Okay, with this we end this part and meet you in the next video. Until then, keep in touch with the Rust, and if you enjoy this video, please do like, share and subscribe to our channel Rust Planet, and have a good day. Bye bye.